begin. Yes. Welcome everyone to the last meetup for Our Ladies Gaborone in 2024. We have Dr. Gwynn Gebeyehu, who will be giving a talk on RN research. And if you've missed it or you want to watch this talk again, you can watch it again right here on YouTube. And I'll let Gwen take over.
Hi, everyone. Good morning, good afternoon, good evening, depending upon where you are. It's really nice to come in and speak to you about art and research. I'm Dr. Gwynn Gebeyehu. I have a PhD in statistics from the University of Auckland. That's where R was invented by Ross Ihaka and Robert Gentleman I want to say in the 90s. After that, I did some work both in industry and in academia and in government. So I've done some I had a research position at Harvard Business School, and then I lectured at Wharton Business School, and now I'm at the Internal Revenue Service, which is part of the U.S. government, and I also I'm CEO of a small business called Perception Analytics that we are also doing some analytics. Today I'm going to talk to you about RN research, and for those of you that don't know, if we can I'm just going to put this in the chat. Can people have I just want an idea of how much what the familiarity is, but how many of you know a little bit about R, or have or know can name an R package? How many of you can name one R package? If you can you please put the name of one R package in the chat? So Jawi, you're asking if I can share again. What do you want me to share? I'm not sure what you're talking about. Tidyverse, good work, Fabrice. So Tidyverse, right? Now don't copy. If you didn't know that there was a package named Tidyverse, don't put down Tidyverse. But is anyone, are there only two of you that know? Oh, Haven, good work. ggplot, good work. Okay, so some of you are familiar with R, so that's a terrific Shinyverse. Yep. Shiny is a definitely package. I'm going to spend some time talking about Shiny today as well, and showing you my my Shiny. I think I'll may show GT. Yes, I think GT is another package. Okay, so thank you to those of you who are participating. I really appreciate it. And I just wanted to get I just wanted to get an idea of how much people know about R, but let me start. So R is a free open source statistical. Yeah, thank you, Simisani, for following up with Jawi. So anyway, R is a free statistical programming language. You can download it from a website called Crayon. You can also download RStudio, which is a really wonderful IDE that allows you to save coding and rerun coding later. It's really a terrific tool used all over the world. It's used in Google. It's also used in Facebook. It's just used everywhere. And it's a really fabulous programming language. So R allows you to do publication quality plots. And you can build them. In fact, the Financial Times gave a talk at Use R, I want to say 2016, that talked about how they use R to produce quality, really high quality plots and publications. You can do full stack development, so you can build some kind of coding, and you can also build a UI, a GUI a graphical user interface using a package called Shiny that it does make it easy for non-R users to interact with it, and it's very extendable. So that's one of the big benefits of R, is that it's not a commercial product, which means that you can write your own packages, wherever, however, and wherever you want. So it's a really great program. And so I encourage you to use it and to start working with it and to get support from your peers to begin to interface with the language. I was at a talk a couple days ago, and it was Douglas Bates, who was an R-Core team member for, I don't even know how many years, up until 2023. I think he's been an R-Core team member for 30 years. And he was saying that he went to Bell Labs in the 70s or something like that. And John Chambers, who invented S, which is an earlier programming language, just started up here and said to him, I'm sure you'll be fine. So I'm going to give you the same message. Just start. I'm sure you'll be fine. I'm sure you'll figure it out. So, and please have the courage to Google, because Google is a wonderful tool. On my resume, I have, languages, or it's something of, I think it's languages that I speak, and one of them is Google, right? Like Google is another language that you really have to learn. So I really encourage you to do that. Okay, so the structure of this talk, let me just go back here. The structure of this talk, I'm going to talk about how I've used R just in publications and in research. One of the topics, the first topic that I'm going to talk about is some NASA data that I did an analysis of. The second one is I'm going to talk about a simulation study that I did, and then a graphical user interface that I did for some a research that I did in during my tenure at UMass Amherst, with a team that was working out of Harvard School of Population Medicine. So, right, so here's the first publication. It's called A Universe of Sound, Processing NASA Data into Sonifications to Explore Participant Response. So this is NASA data from NASA. If you look, Kimberly Cole-Arcan, she's an incredible expert. She's at the Smithsonian Astrophysical Observatory in Cambridge. And Kim is very, very passionate about communicating data to people and really having them engaged. And Kim is a and what she has done with NASA data is just unbelievable. I just think she's incredible. And so I really, I have a lot of respect for her and a lot of time for her. Excuse me. And one of the things that I love that Kim has done is that she's recognized that a whole subpopulation of the world doesn't have visual acuity. They're blind or low vision, and so they can't actually interface with data visualizations, right? And so Kim has extended this this visualizations into something that she likes to call vivifications, which is making it kind of more alive and interfacing. Other people might like to call it sensifications. Doesn't matter, but increasing the population that can actually interact with data. And so she's done really incredible work in this field. So I'm going to share with you let me see if I can do this. I'm going to share with you this this vivification that she's done. So someone's in chat. Is there a question in chat?
Yes, Jawi
Oh, they
wanted
want the
to know.
slides. Yes, of
Yeah, the
course.
slides.
Okay, so let me see if I can go back to get this to, I'll just Google it over here. Galactic Center. Here it is. I think it's this one. And it's a really incredible oh, can you hear it?
Yeah, it was playing, then it stopped.
No, I stopped it. I wanted to make sure that I was sharing sound.
Yeah, it was playing. We could hear it.
Okay, good. Terrific.
Mm-hmm.
And so let me just talk a little bit about how Kim developed this sonification, because she and I have discussed it quite extensively. And so there's only a certain spectrum of light that humans can see. There's ultraviolet light, which bees can see, like there's
Mhm.
and I think you can get a little sense of it with black light, but often flowers kind of, if you look at them under a black light to see the ultraviolet light that they are that they exude, I guess would be the correct word. You can often
Mhm.
see kind of like a landing pad or something. So it's really interesting to know that, there's a whole bunch of light that we just don't see. And so in the spectrum of visible light, it's very much like a rainbow. So it starts with red and it goes up to purple or violet, which they call it. And so what Kim has done is that she interfaced, the mapping that she used, because sonifications aren't one-to-one. There is no standard, right? Like if you're going to plot two 2D variables, right? Two variables, it's going to be an XY chart, right? Or in 3D, you're going to have X, Y, and Z, right?
Yeah.
But sonification is not like that. There are multiple different ways to sonify data, right? And one of the way that Kim has chosen to do this is that she took each pixel and mapped it to an instrument, and she mapped the instrument very similar to the way that the light frequency went. So the color red got mapped to a lower frequency sound, and the color purple or indigo or violet went to something that's like a harp, because harp is the highest frequency instrument. And so
Oh,
so it's a
nice.
really interesting way to think about of sonifying data. And one of the like sonification of data and all of this is, there's just no standard at this point for how to do this. And so there's, you can, if you Google data sonifications, you'll see here, there's just like an infinite number of mappings that are possible. And so it's a very creative space right now. It's not like, data visualizations, I think of them as a creative space as well. But sonifications are just like, there's people doing all kinds of things, and and it hasn't stabilized yet. And perhaps it will at some point. I'm not sure. But anyway, here we go.
Now it's not playing. We can't hear it.
Oh, it's not. You can't hear it?
No, we
Okay.
can't hear it.
That's cool. Thank you for telling me. Let me go back here
Mhm.
and escape,
Mhm.
and then go into my audio,
Mhm.
and then make sure that I'm sharing machine audio settings. Um,
Because like it plays for a little bit and then it stops, like half a second.
okay. Mm.
Let me see if I can try and find it. Data sonification galactic center.
There
Let me see if I
is,
can find it on you.
maybe I need to go into advanced. Let's see, I might need to call, my husband is sleeping because it's early here. Um, I know there's one where you share computer audio. Let me go to general. Maybe it's in general and not in audio. Hmm.
I found it on YouTube. I'm just going to paste it in the chat for everyone to go ahead and listen to. Sounds really nice. Yeah.
Okay. Let me
It's
see
this
if,
is it.
well, I could actually put the link in YouTube if you wanted me to, but okay, I'm gonna change the background noise to low. And then maybe that will help. And let's see if this works.
Okay, now we hear it.
Yeah, so there it is. Oops, let me make this smaller.
Watch why Japanese people eat white rice.
Stop.
Rice is pure glucose.
Okay, so let me go back to audio settings in case there is some background noise that I don't want you to hear. Let me just go down here, close this, and I'll go back into audio settings. And one of the other things I wanted to show you is this. So this is, oh gosh, let me put it in front of me. I have to put it in front of me. So this is a really amazing, this is another thing that Kim Arcan did. So we've done quite a bit of work together. And this is an amazing, this is the, let me see if I can, oh, it's Cassiopeia A, right? And of course, it's only a miniature model of Cassiopeia A because Cassiopeia A, it's another star that she is really excited about. And Cassiopeia A, actually, I think it's bigger than from like the diameter or the radius is even bigger from here than from here to the sun. But it's a 3D print, a 3D model of Cassiopeia A. And she had it 3D printed, and what's really amazing about some of the work that she's done is that because blind or low vision people can't see, but they can have this tactile sense, is that she's taken some of the elements like silicon is a little bit is more of a rubbery element, and so she changes the tactile aspect of it, and copper has a is bumpy and stuff like that. So she's gone as far as to build some of these 3D models so that people can, or blind or low vision, or people can have different ways to interact with data, and it's just really cool. So I wanted to share that with you as well. And so I was really lucky to be part of the group and got to do part of the publication and got to do to analyze the data. And so this is an R terminal here. This is the names. I imported the data, called it data, and this is the names of the data. So this is a unique identifier, collector ID. This is when, oh, actually, you know what? Let me just go a little back a second and talk to you about what we did. And that is that Kim was this, because these, the sonifications were a huge interest to the public, and a lot of people went they kind of went viral during COVID, right? Because she was doing all this kind of stuff before COVID, but you can't actually give people things like this during COVID, right? And so she started building out sonifications, and they went viral on the web. And so she sent out a survey and asked people to kind of watch these 3 sonifications. Galactic Center is the one that we just saw. This is Cassiopeia A. She likes to call it Cass A, and Deep Field. And so there's a bunch of, different sonifications that she developed. And she sent out a survey to people to figure out, how people felt about it. And so she this is the time that they started the survey, that ended the survey, and this is the IP address for the location of the IP address from once the survey was submitted. That we asked about, this is all demographic information. How much do you know about astronomy? What education, gender, and blind or low vision? Do you have blind or low vision? Then what they did was show a sonification, just like I showed you the Galactic Center sonification right now. And it asked, do you enjoy the experience? Hearing sounds, videos, and this is a big one, trusting this representation is faithful to science, right? That's a big one in the US right now. Not a lot of people are trusting science like we would hope. And so then we did all of this work, and then you list up to 3 emotional responses. We did a word cloud of this, and I am motivated to listen more, right? Like, what's your motivation? How do you feel at the end of this survey? And so this is kind of what the data looked like. This is, it was actually a table or whatever, but this is I just want you to have a sense of what the data was. And what was in it. So one of the first things we looked at was a participant count. This is by self-reported astronomical knowledge, and how many blind or low vision responses did we have? So you can see here that we have quite a few kind of hobby or between casual and hobby users, and then there's kind of I guess I'd call this, if it were this way, I'd call it, right skewed. And this kind of, few people think they're experts, and then you have more people who identify as kind of in this area. And I would say that's in both demographics, right? Excuse me. And another thing you can surmise from this, which is really clear, is that many fewer blind or low vision people took the survey than sighted people, which would, align with population estimates of these subpopulations, right? So you'd expect that kind of skew. Okay, but what the question that this article ended up answering was, are there differences in the way that blind and low vision people experienced the vivification, we'll call it, than sighted people, right? And so here is the question. I'm motivated to listen more, and what we see here is that I'm trying to remember what test we did, and I don't off the top. I think it was a Kolmogorov-Smirnov test to see if the differences in the it was a KS test to see the differences in the distribution. And the sighted people and the blind and low vision people had similar, or there was no evidence that of differences in the distribution for being motivated to listen more. But there is differences in the distribution in learning more about the universe. Looks like the blind or low vision people, it really inspired them to learn more about the universe. And it also inspired blind or low vision people. It seemed like they were more interested in learning about how other people accessed information about the universe. So this was a really interesting study. There's a follow-up study that Kim and some of the other co-authors are doing right now on using, I think, comparing color blindness to people with this. So color blindness is people who, it's often Northern European males who have a difficult time and there's a couple different kinds, but I think the most common is that red and green looked quite similar to them. Okay. So now I'm going to talk a little bit about some of the simulation works I've done. So one of the big advantages with R is that if you are developing an unusual design or study, you can do simulations. If you can simulate data, then you can do simulations of trials or research and see what kind of estimates you might get, right? So you can check false positive rates and false negative rates and just work around this kind of issue. And that this is actually what I did for work that I did for my PhD at the University of Auckland with Thomas Lumley. And it was I worked on the clinical use case for this that I'm going to outline is blood pressure. And so blood pressure, it's there's two measurements. There's the systolic measurement and then the diastolic measurement. And the systolic measurement is right when the heart pumps. So when your heart pumps, there's a certain amount of pressure on the blood vessels, and that's the systolic number. The threshold right now for hypertension is for systolic hypertension is 130. And then diastolic is when after the heart's pumped and the blood vessel is more relaxed, they look at, it's called the diastolic. That's the diastolic number. And the diastolic hypertension is when your the threshold for diastolic hypertension is 80 millimeters of mercury. And so this is a measure of pressure. And one of the problems with blood pressure is that it varies a lot. Your blood pressure goes up and down all the time, right? There's rhythms throughout the day, right? So when you wake up in the morning, I think it's, it goes up and then it goes down, and there's just a cyclical rhythm throughout the day, but there's also an annual rhythm, right? So there's it tends to be higher at I think in winter than it does in summer, and so it varies quite a lot. It not only that, but if you lay down, it's different than if you stand up. And if you're above a certain age and someone with a white coat comes into a room, then it goes up. But if you're not, then it goes down. Then it has no impact. So there's all this kind of variation in blood pressure. Not only that, but there's also what we would call traditional measurement error in your blood pressure, which is they did research in Canada, I want to say in the 80s, and they gave physicians a similar underlying blood pressure, and they were to read the they were to give asked them to write down the estimate, and there was wildly different estimates for this. So there's a lot of it's very noisy. And one of the other issues with blood pressure, high blood pressure, is that it's a huge risk factor for death. And systolic blood pressure actually just goes up as over time. It's about 1 to 2 millimeters of mercury. At the population level, it's about 1 or 2 millimeters of mercury for a year. So if you live long enough, you're very likely to be diagnosed with systolic hypertension. So that is something, and it's a huge risk factor for death because it's, the blood vessels can break, and, you can have a stroke or all kinds of problems. So it's something that you really, really do not want to have high blood pressure. And so one of the medications that the pharmaceutical industry has is, blood pressure medications. And one of them is called candesartan. And the thing about these blood pressure medications is if you begin to take them, you're really on them for the rest of your life because your blood pressure has such an increase in over the years. Now, but as you know, this is of course, economically beneficial for the pharmaceutical industries because you do have to take it for the rest of your life. But people do have to reach this certain threshold of blood pressure in order for them to take it. So one of the questions that has been asked is, if you start taking the medication earlier, is there any kind of long-term benefit, right? So if you take the medication for a certain amount of time, is there a long-term benefit in taking the medication after treatment ceases? So I hope, so graphically what I'm saying is this is systolic blood pressure. Here is the trend as we increase in time. At this time, the guidelines were that you were hypertensive when your blood pressure was at about 140, right? That was the threshold. So this person is pre-hypertensive. They have a systolic blood pressure between 130 and 139. And this is the true underlying blood pressure. So this is without noise. And here we take this medication and immediately the treatment works. We know it's effective. And this is someone who took blood pressure medication for 2 years. And then the question that that a pharmaceutical industry might ask is, what does the return to prior trend look like? Is it, does it go immediately back to the prior trend, or is there some kind of delay in returning to the prior trend? And here are some opportunities for what the delay might look like. It could be this could be, a 6-month delay up to a 2-year delay, right? So this was a clinical question that was addressed in a trial called the Trophy trial. So it's a trial of preventing hypertension. And the clinical question was, if you give someone medication who does not have hypertension, is not yet diagnosed, but is close to the threshold, is there a long-term benefit? And that long-term benefit, this part right here, is called the carryover effect, right? So does it go back to the prior trend quickly or more slowly? And so that's the clinical question. And so the Trophy trial, or trial of preventing hypertension, asked, can treatment with candesartan delay the onset of hypertension? And so it was actually 809 people who were randomized to treatment or control arms, where the treatment arm received 2 years of medication, 2 years of follow-up, and the control was monitored for 4 years. And the p-value, they did a t-test on the number of people who were diagnosed with hypertension, and found that the effective active treatment on delaying the onset of hypertension can extend for up to 2 years after discontinuation of treatment. So based on a t-test on the number of people who were diagnosed with hypertension, we have some kind of delay in the return for the prior trend. That's what this simulation, what this study said. And it was published in the New England Journal of Medicine. It was a very high impact paper, and people studied, went, all over the world and did a lot of presentations on it, and encouraged physicians to prescribe candesartan to people in pre-hypertensive states, right? And so this was a huge economic boon for This was done by AstraZeneca. For AstraZeneca, because prior to this, only people who were hypertensive could be prescribed this medication. And now people who are pre-hypertensive can be prescribed the medication, right? So what that means is that they have, you know, millions of more you know, of doses being taken, which increases their profits. So this was a big economic boon. The statisticians that worked on this trial were actually at the University of Michigan. So I'm just going to outline the trial again and talk to you a little bit more about it. So this is a trial of preventing hypertension. There was 809 participants with systolic or diastolic blood pressure in this certain range, which is 130 to 139 millimeters of mercury. The treatment was 2 years and 2 years of follow-up, just like this here, right? This is someone in the treatment arm. They had 2 years of candesartan, and then there were 2 years of follow-up. The placebo arm only had 4 years of monitoring, and there was measurements every 3 months. So 69% of those who were diagnosed with hypertension did so by having 3 measurements above 140 millimeters of mercury, right? So there were 3 measurements above the threshold, and that's how they were diagnosed with hypertension. The treatment arm, there were 53.2% that were diagnosed, and the placebo arm had 63% that was diagnosed, and that was a cumulative diagnosis. Okay, so let's talk a little bit more about this study, because I want you to have an understanding of why of what my dissertation was. So what we have, this is a person, right? Here's this threshold, which at that time was 140 millimeters of mercury. And this is a person, this is their blood pressure. And okay, so now they have 2 measurements above the threshold. Please put in the chat, are they diagnosed with hypertension or not? I'm going to look up in the chat. Are they diagnosed with hypertension or not? If they have 2 measurements. Right, exactly, Razia. Thank you for listening. I just want to make sure that you're understanding. And Razia, can you tell us why? Why aren't they diagnosed?
I hope you don't mind, I've unmuted. I think you
No,
said
I'm glad
3
you did.
measurements.
What?
I think you mentioned that 3 measurements were needed to be diagnosed.
Absolutely. So you have to have 3 measurements above the threshold in order to be diagnosed. And that was for 69% of the people that were diagnosed that way, right? So you have to have 3 measurements above the threshold to be diagnosed. So this person wasn't diagnosed ever, okay? So let's look a little bit at blood pressure and think a little bit about the context of this study and this research. Does anyone else have questions about anything I've said so far about this study, or no? Okay, you're okay. Everyone's good. Okay. So let's keep going, because this is the important part, and I want to get to the good stuff. So here we have this is the blue is someone who's, you know, in the placebo arm, right? And this is the treatment group. So here we have someone who's been taken treatment for 2 years, and then they have 2 years of follow-up. This is someone who's just being observed for 4 years. Now, but this is the long-term average, right? This is a long-term average, but this is a number that we do not know. Why not? Because blood pressure varies a lot, right? That was one of the first things I talked about. So we have all this blood pressure issues. It varies a lot. So this is, you can see here, this underlying blue, right? And here we have red. So we end up getting all of these blue dots everywhere and red dots everywhere. And this is a really small measurement area. It's 3 millimeters of mercury per, you know, the standard deviation is 3 millimeters of mercury, right? So it's a really small measurement error, but you can still see that it's very challenging to see the underlying averages, right? So here, this goes up and down and up and down. It's all over the place, and you don't really know, and you don't really know what the actual value is, right? So we have all of this noisy measurement. But then we have this this added issue that I want to say her name is Reza. I hope I got that right. That Reza brought up, which I told you, which is that we have to have 3 measurements. Most people were diagnosed with 3 measurements above the threshold. So we have this, and then we have 3 measurements above the threshold, right? So here's this blue person. Okay, so this person is diagnosed on this one, and the red person is diagnosed. This person's diagnosed, right? This is before the trial. This is right at the start. So they're diagnosed after 1 year of treatment. This person gets a little bit longer, right? Because they're in the treatment group, right? So their treatment is actually, for the duration of treatment, right? What happens? Their blood pressure is lower because they're taking medication, right? So on average, we expect their blood pressure to be lower. But then what happens next? Well, in order to get IRB approval, you can't let, hypertension is a huge issue. It's a huge risk factor for death. We can't let people just in our study have hypertension and not treat them. So we have to treat them, which means what? That we have, after this measurement, we have to start giving them some kind of additional medication so that their blood pressure is lowered. So we have a much more complicated data structure than what we might have expected. So we started like this, right? We have this long-term average trend. And what do we have here now? Now we have this, right? So we have to take into account noisiness. There's a lot of noise. We have to take into account that the measurements, the way that they measured diagnosed hypertension. You have the noise, the way that they diagnosed hypertension, which is 3 measurements above the threshold, and then missing values, right? And so this makes everything extremely complicated. And what I want to point out to you here is that in this time frame here, the measurements on average are going to be lower, but only because there's treatment, right? What they were trying to test, the hypothesis that they wanted to test, was this carryover, this long-term impact, right? But they've never tested that. Why? Because they didn't take into account this noise, this measurement, and this missing value. Does that make sense? Any questions there? So this trial design had an 80% false positive rate, right? So what's the trial? What's the value for that we usually look at for a false positive rate in a trial? Anyone? It's the alpha value. I'll just say that. Okay, it's 5%. It's 5%. So the alpha value that we usually go for is 5%. So that is, we expect it to be about, 5%. But this has an 80% false positive rate because people are, because the treatment group has a lower blood pressure for the duration of the treatment effect. And that is regardless of whether or not there's any long-term impact after treatment has ceased. Okay. So this was what my dissertation addressed. And we did so here's the parameters for the trophy trial. We randomized 800 participants. So we've simulated these trials with systolic blood pressure between 130 and 190. The treatment we varied the treatment effect. So you could have, the length of treatment. So you could have 5 months, 6 months, a year, year and a half, 2 years, and 2.5 and 3 years, right? So we varied it a lot. And then And then we had the placebo was always just 4 years of monitoring. The measurements were every 3 months, every 6 months, or yearly. And 69% of those diagnosed with hypertension did so by having 3 measurements. I'm sorry, and the rules for diagnosis, right? So you could have 3 measurements above, you could have 1 measurement above, and then we did some averaging. So you could average 3 measurements above or average 2 measurements above. The treatment, and we kept track of how many people were diagnosed in the treatment and the placebo arm. And we found that, and we also did a crossover study, which is that, you are randomized not to treatment or placebo, but to treatment first or treatment second. And none of that worked. So if you want to do a t-test to test for this is not the way to do it. The other thing that we did is looked at this differently and used a mixed effects model approach. And the mixed effects model approach worked, actually. We used a parametric bootstrap so we fit the model because the model factors into a probability of missingness, right? Because this data is really, it's missing at random. Here, the data after treatment, after diagnosis is missing at random because we know why it's missing. We have a construct of why it's missing. And so the likelihood factors into a probability of the blood pressure, and then a probability of missingness. And so you are able to address it with this model. And then you do a parametric bootstrap for the relative risk of hypertension for the first time point after treatment ceases. And if the relative risk is 1, then there's no carryover. And if it's bigger than 1, then there is a carryover. Something you want the script. Well, there's going to be a recording. Is that what you're talking about? Or what do you mean, Fabrice? I'm not sure. Okay, so let's just take a big breath. The next one is going to be a little bit easier. It's not going to be as technical. And I'm going to talk a little bit now about the shiny GUI that I built for cluster randomized control trial. So there you go. Simsani, do you want to have a little break, or should we keep going, or what do you think?
How long is how many slides do you have left? Do you think we need one?
Let me see if I can here's the shoot. This is not what I want. I want the burger. Here's the burger. Let me close this. I don't think I have many slides left. Here we're on this slide, and I have 1, 2, 3, 4, 5, 6, 7.
Okay, I think we can keep going.
Okay, let's keep going. Okay, so in a cluster randomized trial, does anyone know what a cluster randomized trial is? Can you, do you want to, can you put that in the chat if you do know what a cluster randomized trial is? What's a cluster randomized trial? Okay, it doesn't look like anyone knows. Oh, a trial that randomly selects. That's a good guess. Absolutely. So I'll just talk. So I'll just add a little bit more. So you have a cluster randomized trial versus an individual randomized trial. That says trail, not trial. Anyway, it's supposed to say trial. Any guesses what the difference might be?
I think it means in a, let's say, in a hyperspace, you have a, well, in a search space, you have all these different values or points, and you just randomly group them. I think that's the cluster randomized trial.
It's much simpler than that, Simasani.
Okay.
But I love it because that's exactly what I would do. I would think of something much more like it's much more complicated than it is. That would be my first guess too, is to think too deeply.
Okay.
Yes. Yes. So grouping of subject in groups, right? So that's what it is. So a cluster randomized trial is a type of study where groups of participants are randomly assigned to different treats rather than individual participants. Right, exactly, Fabrice. This is what it is. And Red Cap does a good job at that. Okay, I believe you. So anyway, sometimes you have an intervention. So sometimes you have an intervention that you want to do like at a population level, right? For example, you have a new teaching method. Well, you can't or a new teaching something or other. What you would do is you would and the impact of that teaching method might bleed over into other classrooms, right? Or into other students, right? You have a classroom, and if you're teaching like half the class one way and the other half the class the other way, it doesn't really work because it could bleed over into each group, right?
Mhm.
So what you do is you have to randomize by like school district or school or something like that. So although you may have a number, like you may have, 300, I don't even know, 300 people in each school, then the units that are randomized are much smaller, right? You might only randomize like, 20 schools as opposed to, five, the 10,000 students that you're teaching, right? So it's just like, so it's a different kind of trial. And I'm going to talk to you about two of them right now that were done before I arrived. This is something that's out of Harvard. Harvard, it was done by Susan Huang, who was, I think at the time that this was published, it was at Harvard School of Population Medicine. And so it was a 3-arm trial. It was a reduced MRSA trial. I don't know if you know, MRSA is multi-drug resistant Staphylococcus aureus. And what has happened at the world level is that they developed antibiotics. Wonderful. There were so many people who were healed, but the bacteria have begun to understand, have begun to mutate because of all of my antibiotics that people are being given, if that makes sense, right? So the bacteria itself is mutating and becoming resistant to drugs. That's why it's called multi-drug resistant, right? So it's a disease and an infection that that's very dangerous and can be very harmful for people because these are antibiotic resistance. And so anyway, and the point is that they don't want it to spread anymore. It's really important that it not spread, but one of the problems is that it in intensive care units or emergency rooms in hospitals and also in nursing homes, there tends to be, it can tend to be spread more easily. And so this research group they're infectious disease physicians, infectious disease physicians, and they're trying to figure out what methods can be used to reduce multi-drug resistant Staphylococcus aureus infection rates in hospitals. So it's a 3-arm trial. The reduced MRSA trial is a 3-arm trial, and there were the first group was these hospitals or ICUs I can't actually remember which one it was in this one, but they screened all people who came in for MRSA, and they screened them, and then they isolated. The second group was they did targeted decolonization, which means that they did nasal swabs with some kind of antibiotic to reduce this. And then they did bathing with, it's called chlorhexidine, right? So there was they screened people for this, they isolated them, and they decolonized the carriers of MRSA. The third group was universal decolonization. Everyone had given nasal swabs and also bathed with chlorhexidine. So in the third group, there was a huge reduction in the incidence of MRSA, right? So that means that this is a good study. It was a really influential study, and they were able to reduce the spread of this horrible virus, or bacteria, I guess, this horrible sickness. So one of the problems with this is that was addressed with this is that at baseline, this is one criticism, is that at baseline, the third group had many more cases of MRSA than the other two arms, right? So the issue that that one of the questions about this study was, is this due to regression to the mean as opposed to the impact of the universal treatment? So what that meant is that since they randomized, like 20 or 30 different hospitals, right? If you're randomizing, 10,000 people, you randomize one person to a treatment or control, you randomize each person to a treatment and control arm, you can assume that there's a lot of similarity between these treatment and control arms because there's so many participants, right? But if you're only randomizing 20 units, it's more challenging to get things matched at the population level, to get, to assume that they're exactly the same, right? And so in this trial, the matching at baseline, the baseline group, the baseline groups at the groups at baseline were different. And so that what they wanted to do, or what we needed to do, was try to develop a way to make sure that when you randomize, you're going to get a similar, the groups are going to be similar at baseline, right? So you need to kind of restrict this because you're matching so many the units that you're matching are so much smaller, right? So with this, I developed a shiny application, which is not coming up. Where is it? Oh, here it is. I guess this is so here's this shiny application that I developed. And so the shiny application, what it does is, and I'm just going to load the data. I'm going to put in 5 variables. And what it does is it practices randomizing, right? So it allows clinicians who are doing this kind of research and doing a group randomization to randomize with some level of confidence that their baselines are going to be similar, right? So here I hit go, and all of this is done in R. And you can see that this is, I'm going to put this to 45 or something. I was just playing with this last night, so I have some ideas of what it looks like, right? And so what this does is it matches, right? So here I have hospital 1 matching with hospital 32. Well, hospital 1 gets randomized to treatment or control, and hospital 32 goes to the other arm, right? So it allows you to pair, and this is done in this general inputs tab. It's done 300 times, right? So I've randomized one hospital. I've randomized, let me see the matches. I randomized all of these, right? These ones here, and then the leftovers just get put to the other arm, right? And so I am randomizing, but I'm randomizing with a little bit of restriction so that I can figure out what pairs, what weighting or what pairs are going to give me the best similarity in the baseline variables. Okay, so for example, maybe I decide that attributable days per month is a really important variable for this research that the treatment and control arm really need to match. So then I just change it, and maybe I can update this to 5, and you see what happens here is that now I have to deal with, well, now this outcome is more spread apart, right? So I'm looking at this kind of multi, you know, nth degree. Well, in this case, it's actually 5, right? This 5-dimensional space trying to figure out what is the best pairs for matching, right? And so here, instead of being the other hospital, I don't remember what it was matching with before, it now matches with something else, right? One is now no longer with 39. It now matches, I'm sorry, one was matched to a different number earlier. Now it's matched to number 39. So you see that this is just a way to figure out, I'm just going to go back to 1, and then you can see that this will no longer be 39, it's 32, right? And so what you're doing is you're updating the matches and trying to, and so the researchers were really happy with this. You can also look at this a different way. Here's you know, like here's this one, right? You can look at this, and so you can see if it's low here, is it high over there? What, you know, it's just a way to kind of look at the different distributions and see. You can see that this is yellow here, this is over here, you know, you can look and see what this multi, you know, this 5-dimensional space looks like, right? And so and then you can do randomizing and all kinds of other things. So anyway, this was a really important piece of research. The trial designers were really happy with it. It went straight to the CDC, and they were they thought it was really incredible. And they've been using it ever since. So let me just go back here. Here we go. And then let's see if I can get to the next slide. I don't want to annotate. Go away. I don't want to annotate. This is like really annoying. Here we go. I want to go to the beat. Let me close this. I want to go to the, this drives me crazy. Can you see this annotate is right where the burger is, and I can't get to the next slide. So let's see. Let me just try and go to 14, or let's see if I can do that. So anyway, this was published in here in this article, and it's been used for all subsequent research done by these authors, Susan and Richard and Ken, right? So they're Ken and Richard is also, Susan is at UC Irvine, Richard is Harvard School of Population Medicine, and Ken is at UMass Amherst. And so they have a whole group, and excuse me, and they do a lot of and this is a very influential paper. It was a Journal of American Medical Associates, a very high impact journal. And so this tool is used all over in this research group, because it's very important to be able to match at baseline. And in fact, Shruti won an award for this one, so we're really proud of her. She did a great job. Okay, so that's all I have. I'm done. So if you have, I'm going to stop sharing screen. Hope it wasn't too long. people aren't sleeping.
No, we're all here. I've got a question for your shiny GUI.
Oh yeah, it's gooey. Gooey is the way that's pronounced. Go ahead.
Oh, GUI. Oh, okay. Right. I wanted to ask about when you were setting the values. Is there a machine learning model behind it? Because it trains itself. You were saying something about it training itself, or it teaches itself how to predict the values.
So this is what it does. Let me see if I can try to remember what it does because I did this so many years ago. But what it does is that it goes into uh, a space and it looks at there is it isn't a machine. I would call it more like a permutation test as opposed to a machine learning model. But in these days and age, most people would call it artificial intelligence, right?
Okay.
But because of this, but it does allow people to kind of randomize with some sort of confidence, but it's it does go into there is some mathematical model behind it that I did not develop. So it uses a package called, actually, you know what? I could look it up because I have it here. It's in GitHub. The coding's in GitHub if you ever want to look at it.
Okay.
Yeah, you can
And
totally look. In fact, I keep wanting to make a package over it for it, a GitHub package so that you can look at it. But here it is. Oh, here it is. This one. Here's the Goldilocks. Here it is. I'll just put the package. This is where the coding is if you want to look at it. And then it's deployed here.
Okay. Good luck to all. All right. Let's see it. Okay. Right, it's opening. I see. Are there any other packages you used in the study?
Yes, I did. I used, and we'll show you let me think. Which one of these is the one that tells you which packages, the necessary packages? Let me just go in the server. I think it's in the server. Am I right? Nope, I'm wrong. That's in the pack. It's in the UI. And yeah, the matching is done in a different package. My addition to it was really the interface, the graphical user interface, or GUI.
Okay.
And so, but the matching is done someplace else. I can't remember.
Oh, okay. I see it.
Actually, let me just look at it locally because it'll be easier for me to remember there. Because it's,
Oh.
I think. But anyway, sorry for my my not remembering this, but it's here it is. Well, design match. It's in the design match package. That's done in the design match package. I'll just show you.
Yeah.
I'll just put that in there. So you can see it. Here it is. So it uses this package.
Oh, did you share it in the chat? It's not shared.
No, I'm putting it in the chat. I just found it on.
Okay.
Yeah,
Oh,
it's
there
by
it is.
Jose Zubizarreta. He's I think he's Chileno or something, if I remember properly. He's from Chile. He's I
Oh,
think he
okay.
was,
I see it.
Yeah, and so it uses that package to do it, and it was I don't really even know what it did. It was just like,
Mhm. Okay, that's cool. I like how all your studies are open access.
oh yeah, no, I
Mm.
just it's just so important, we're all just like, trying to work together.
Mhm.
Yeah, I mean, the only reason I haven't made it a package yet is because I'm a little scared of all of the crayon people.
Look, what do you mean? Is it all the reviewing and does it take long to come out?
But the crayon people have told me, Gwen, you should just submit it. We're very nice. We're much nicer than you might think, as long as you don't have C coding in it. So I usually have a project with the crayon people, but
Right, right. How long do they take to review it?
I don't think very long. And
Mhm.
I think because my this package doesn't involve any C or anything like that, that I don't have to change compilers. The R core people are nice enough to update the R itself whenever there's a new chip. So we're really happy. We're really happy for the R core team so that we don't have to do that. So yeah.
Okay. Oh, all right. I think I'm okay with that. Thanks for sharing. Do we have any more questions, comments, suggestions for Gwen? Now is the time to ask.
Oh, hi, Francis. I didn't see you there.
I'm just kind of following Keely. Um,
Oh, Francis is here.
Thanks for coming, Francis.
just picking up
Do you have,
takeaways.
Yeah, Francis, be careful. We were just talking about the in DCR, there's a big flu outbreak. So everyone just be careful. We're all thinking of you. I don't know if you've heard of that.
Francis, do
It's
you
done
have any?
elections pretty early.
Do you have any questions for Gwen? Any comments, suggestions? Razia?
Oh no. All my questions has been answered. Yes, all has been answered. Along the line, it was about this randomization. I did a project some time ago in Ghana, in the northern.
Mm-hmm. Okay. So, Francis, what we got is that you did a project and we
I
can't hear
think
you right now. I think we can't. Thank you, Francis. I think we can't get you. I think it's because of the network, but we did hear that you were doing a project that's related to Gwen, and I think yeah, you do keep in touch with Gwen. I think so. Do we have any questions, comments? Fred, Isaac, Sibongile?
Gwen,
Yeah, hi,
sorry.
Razia. I noticed you were
Hi, I
unmuted.
don't have a comment or suggestion, but I just want to thank you for your very interesting talk. I'm
Oh,
also
I'm
in the health field, so I could relate to some of it.
yes. Thank you so much. Thank you. Thank you for coming, Razia. Where are you?
I'm in Gaborone.
Oh,
Oh,
okay.
she's on Gaborone. Okay, that's so cool. Thank you, Razia.
Are you too, Simi?
Yeah, I am. I'm in Broadhurst. Where are you?
Phase 4. I would love to meet up with you. I actually know your sister Chenjilani very well.
Oh,
Oh, yeah, I
wonderful.
thought your name was familiar. You went to New Era Secondary School, yeah? You guys were in the same class.
Yeah, we were in together at Lehigh Academy.
Mm,
Oh, right. Okay. Yes, we can definitely meet up next month because it's the holiday. I'm at UB, so we can definitely stay in touch.
mm,
Sure, yes, please.
mm.
Yes. Thank you so much. Oh, that's so cool. She was my sister's classmate. I think they were kind of
Yeah, isn't
friends. Her
that
name
wonderful?
sounded familiar. Yeah. Any
Mm.
questions? Any comments? Gwen, are you comfortable sharing your contacts if anyone wants to reach out to you?
Sure, you can email me here.
Okay.
I'll just add one more thing, which is congratulations on getting married recently, Francis. We
That's
were all
right. I did see that.
excited for
Congrats,
you.
Francis.
You know, finally you're a grown man. We're really excited for you. It's
Yeah.
wonderful.
I still. Really getting me blushing.
Yes, of course. Very important to honor them.
Right. I
That's
think if we don't have any more questions and comments, thank you everyone for coming, and we'll see you next year. And please keep in touch. If you have any questions, comments about the talk, you can reach out to Gwen. If you have any questions about anything R related or data science related, you can reach out to me, or you can send a message to Gaborone at ourladies.org. Let me just write that in the chat. Yeah, there we go.
Gaborone.
Yeah, Gaborone.
Is that French or what is it? Is that
No, it's Anna. It's
Botswana? I've never even
it's
heard
Anna,
of that.
yes. You haven't. Gaborone, yes. The G is like you're goggling, so you stretch the G.
Mm.
Thanks,
Okay.
everyone.
Talk to you all later.